Well, as Governor Noem has clearly stated, we will not have school we'll not have in-class school the entire month of April. So, back to the old drawing board, or whiteboard as the case may be. So today we're going to do 12-2, Evaluate Limits Algebraically, page 742 for pre-calc. Okay. So, we've talked about limits before, we're back in chapter 1, and now we just started getting back into it with last week's section, chapter 12 to section 1. The main concepts we want to use is what's called the limit of a constant. So, if I'm doing a limit as x approaches c, but all my function has is k, just some other number, all I'm going to get is k. Now that seems kind of goofy, but let's give an example. If I'm doing the limit as x approaches 3, because c again is also some constant, and all I have for my function is 4, well, all I'm going to get is 4. There's nowhere for me to input that x in there. So if I'm doing the limit as x approaches something, but all I have is just one number, there's nothing for me to really do, so my limit just has to be that number. Okay. And the other main one, before we start getting into some of the how they combine and interact with each other, is the limit of the identity. So, if I have limit as x approaches c of x, all I'm going to get is c. So again, let's talk about an example. The limit as x approaches 3 of x, well, x is a function. We know that those limits exist. And if I were to do the limit of it, it would approach 3 from both sides. So those are the main two that we start with the backbone of. And now we get into sort of how they interact with other things and how operations affect them. You know, your multiplications, your subtractions, your additions, and then like your power rules. Okay. So, the rules we're going to start with, well, an easy one to start with, what's it officially known as the sum rule. Well, sum rule is pretty easy. Remember, sum just means addition. So if I have the limit of f of x as x approaches c plus the limit of g of x as x approaches c, I really just have the limit of, as x approaches c, of f of x plus g of x. Now there's an equal sign, meaning you can go either directions. What this means is if I have one limit and I have a big long expression, I can just break it apart into smaller pieces and work with it that way. What would be a quick example? What's the limit of, as x approaches 2, of x plus x? I can break that apart into two separate equations, my f of x being x, my g of x being x, instead of just having one long thing. Now this one is not a very great example because you would just combine terms, but that would get on to something else. Okay. We also get the difference rule. So again, the limit as x approaches c of f of x minus the limit as x approaches c of g of x. Now you're going to probably start noticing, and then of course it equals the limit as x approaches c of f of x minus g of x. Now you're going to see a pattern probably starting to establish. Our limits have to be the same thing every single place in one equation. So if I have x approaches c here, it has to equal there and there for the thing to hold. You cannot have as x approaches 0, as x approaches 1, and then as x approaches 2. It just doesn't work out that way. Let's see. We also have the scalar rule. So the limit as x approaches c of k f of x equals k times the limit as x approaches c of x. So all that means is if I have a scalar function out front, like a coefficient, I can just boot it out front and worry about the x parts first. So if I had something like the limit as x approaches 2 of 6x, I could just kick my x out, or my 6 out in front, and then I could just do the limit as x approaches 2 of x. And then I just multiply by 6 later. That's all that means for that scalar rule. Now we're going to get into the product rule. So the limit as x approaches c of f of x times the limit as x approaches c of g of x equals, well, you guessed it, I can combine them into one expression, f of x times g of x. If they're being multiplied together, I can separate them, even if they're functions, not just if they're scalars. Shoot. Well, if we have adding, subtracting, and multiplying, of course we're going to have dividing. Now dividing is called the quotient rule. So, if I have the limit as x approaches c of f of x divided by g of x, then that's the same thing as, how do I write this again? Oh yeah, I just write it as the limit of f of x as x goes to c divided by the limit as x goes to c of g of x, as long as I have one specific thing. G of x cannot be 0, and as you can guess, it's because I cannot divide by 0. Therefore, also the limit as x approaches c of g of x cannot be 0 either, because again, can't divide by 0. That causes some issues, which we'll get to later in the section. Oh, and one last one we have is called the power rule. Power rule. Power. It says that the limit as x approaches c of f of x to the n equals, if I did the limit first, x approaches c of f of x, and then I did the power. So the order you do the power doesn't necessarily or technically matter. For an example, let's just use x squared. So the limit as x approaches 2 of x squared. Well, I would just do, I could do the power later, so I could do the limit as x approaches 2, which I get 2, and then I would do the power, so 4. And which would make sense if we did the graph, we would know that it also approaches 4. Okay, those are all the rules here that we're going to incorporate into solving some limits algebraically, as opposed to what we did previously, where we're just finding a graph and then plugging in and making those charts. Okay. example 1, algebraic limits. So let's see, we're going to find the limit as x approaches 4 of x squared plus 6x, minus 6x plus 3. Okay. So again, the important thing to note is this is going over the entire expression, not just the first one. And using those rules, well, first I can use the sum and difference rules, which says that I have subtraction signs so I can break them apart, I have addition signs so I can break them apart, so I get the limit as x approaches 4 of x squared minus the limit as x approaches 4 of 6x plus the limit as x approaches 4 of 3. Now here, power rule, so I would do the limit part first, power rule. Here, I have the scalar rule, so I gotta take my 6 out in front, so 6 times the limit as x approaches 4 of x. And here, I don't have to do anything else fancy. So plus limit as x approaches 4 of 3. And here, limit as x approaches 4 of x squared. Okay. So now we get some interactions from our previous things that we talked about. We have the identity. Yeah, so I get x is approaching c, and then I get an x. So my answer is just going to be c, in this case, 4. Then I get 4 squared, which is 16. Here, I'm going to get that minus 6 times whatever I get in here. Here again, I suppose I put it up here. 6 times whatever I get in here. Again, as x approaches c of x, so my answer for here is just going to be c, so 4. 6 times 4 is going to give me 24. And here I get as x approaches c of k. Now remember, if k is just some constant, there's nowhere for me to plug it in. So all I get is just that constant, so plus 3. So I get 16 minus 24, which would be negative 8, plus 3, which would be negative 5. So yeah, all we did was sum and difference rule there. Sum diff to break them apart. Here we did the power and scalar. And then on this last step, we just talked about the identity and the constant. So that one's a good example because it incorporates everything except for the quotient and the product. Those would work the exact same way. Now some of you might be seeing some sort of easier way to do it instead of breaking all down this, is what ended up happening is we ended up just plugging in 4 for everywhere we saw x, and that will work pretty often. That's a quick way. As long as it's a function that has limits, we just do, it's the quickest way. It's called direct substitution. When in doubt, you can just do direct substitution. Now in that specific case, it would have worked right away. We had x squared minus 6x plus 3 as x approaches 4. So I get 4 squared, 16, minus 6 times 4 is 24, plus 3 would be the same thing. So quick, we use direct substitution if we can. The only problems are the problems we get a whole bunch when we get all those algebra. We can't. No dividing by 0. And no negative radicals. So those are the problems with direct substitution. If you don't have anything like that, just plug it in right away. Just go for it. Let's see, example 2, direct substitution. Okay, so let's see, we get the limit as x approaches -1 of the equation -3x to the 4th plus 5x cubed minus 2x squared plus x plus 4. Okay. This is a perfect candidate for direct substitution because, well, frankly, I could break each of these down. I could get -3 times the limit of x is to 1 to the power of 4. I could break down with all those rules, but it's just easier if I just directly substitute. Because again, I'm not going to divide by 0. There's no x's in the denominator, and there's no radicals or square roots that I'm going to get a negative of for imaginary numbers. So I can just direct substitute. -3 to the power times -1 to the 4th plus 5 -1 cubed minus 2 -1 squared plus -1 plus 4. Okay. Well, -1 to the power of 4, that's the same thing as +1 times -3 gives me -3. -1 cubed would be -1 times -1 times -1. So I would get a -1 overall. Times 5, so -5. -1 squared would be +1 times 2, but it's a -2, so I get -2 again. -1 plus 4. -3 minus 5 is -8. -10, -11 plus 4 would be -7. Okay, just simple order of operations, and remembering the -1s would alternate. So like -1 to the power of 1 is -1, -1 squared is +1. The big thing is, in your calculator, if you're double checking with something like -1, be sure to put brackets around, or brackets or parentheses, some grouping thing, because a lot of times when you type in something like -1 squared in your calculator, it's going to give you -1. The reason it does that is because it says the opposite of 1 squared. So it does the 1 squared first, which would be 1, and then it does the negative value. So you have to tell your calculator specifically, no, I want to square -1, the opposite of 1. Is how those calculators are programmed. Now, direct substitution helps us in a lot of cases, but not all of them. Namely, dividing by 0 in radicals. So we have to figure out ways to get around those. Well, first we're going to talk about what's called the indeterminate form. The indeterminate form is when you direct substitute, and it gives us 0 over 0. Okay. This isn't very good. An example of this would be something like the limit as x approaches 1 of 2x minus 1, 2x minus 2, over x minus 1. So if I were to directly substitute, I would get 2 times 1, which would be 2, minus 2, so I'd get 0. 1 minus 0, I'd get 0 on the bottom. That'd be the indeterminate form. Okay. So there, since we're dividing by 0 in our limit idea, we cannot actually accurately describe the limit. So we have to do some different steps. Namely, we get to do some algebra. There's a couple ways we can do this, so let's get into it. Example 3, use factoring. So let's say we have the limit as x approaches -4 of x squared minus x minus 20 all over x plus 4. Okay. Now, if we didn't know it was an internal form, we check it. So I get negative 4 squared minus negative 4 minus 20. Negative 4 squared would be positive 16. Minus negative 4, the same thing as plus, so I'd get plus 4 minus 20. 16 plus 4 would be 20. Minus 20 would be 0. Negative 4 plus 4 would be, again, 0. Indeterminate form. So now we know we have to do some algebra to see if we can figure out a way around that. Just because that point doesn't exist doesn't necessarily mean that the limit doesn't exist. So, let's see. Well, we can do some clever algebra. We can factor this top part and sort of see what happens. So if I were to factor this, I would get x plus 4, x minus 5. All over x plus 4, because I haven't done anything to my bottom yet. Now, algebraically, what is x plus 4 divided by x plus 4? I don't say 0, okay? It would be 1, so I can simplify them both out. It's like if I had 4x over 4, I could cross them both out and just have whatever's left. So, my limit as x approaches negative 4 still holds, but all I have left is my x minus 5. And then now I can just do direct substitution. Negative 4 minus 5, so my limit would be negative 9. Now what would happen graphically is if I had this, I would have some graph, let's see, at negative 4 has to be negative 9. Not exact, just ballparking it. So at negative 4, say it was here, I would just have a hole in my graph, but if I were to look at it, I would still be approaching that negative 9 value from both sides. That's what's happening. We just did that without it actually graphing it. I would have a hole in my graph because, again, I can't divide by 0, but my limit still exists and I'm approaching the same value from either side. Example 4, we're going to use rationalizing. So let's say we have something like the limit as x approaches 9 of the square root of x minus 3 over x minus 9. Well, again, when in doubt, direct substitute. So I get the square root of 9 minus 3. Well, square root of 9 is 3. 3 minus 3, 0. 9 minus 9, 0. 0 over 0. Indeterminate form, no bueno. Okay. And with this one, there's not really much I can factor with it. So here I actually get to rationalize. Now normally we've always tried to get rid of a radical. We've always rationalized the denominator. In this case, it just happens that we have to rationalize the numerator. Now remember, to rationalize, we multiply by the conjugate. So I look at my radical, or where it's at, and I'm going to multiply by my radical, of x in 3, and then x in 3. Now I look at this value, and I always flip it. So this is a subtract, so I'm going to have plus signs. The reason I can do this is, again, square root of x plus 3 divided by square root of x plus 3. Again, it's the same as the top and bottom, so it has to equal out to be 1. So I can just multiply by that value without changing the integrity. And then now it's just a matter of foiling or distributing. I get square root of x times the square root of x. Well, that's just going to be x. I get negative 3 times the square root of x, so negative 3 square root x. I get x times positive 3, so plus 3 square root x. And then I get negative 3 times positive 3, which would be negative 9. Here's the real reason we want to multiply by the conjugate. If you multiply by the conjugate successfully, this happens, where my middle terms would simplify out. So now all I have is x minus 9 for my numerator. Now to the denominator, unfortunately here, because I don't have a radical or a conjugate to multiply that, I'm going to end with a radical, but let's see what happens. So I get x times the square root of x, so x square root of x times 3, so 3x, negative 9 times square root of x, so minus 9 square root x, and then negative 9 times 3, so minus 27. Okay. Now again, messy, but we'll see what happens here. From the top, I get x minus 9. So I would direct substitute, I guess this whole thing go right here. I'm just going to keep it over here, not rewrite it. Okay. So x is 9, right? So 9 minus 9, so my top is going to be 0. Now if I do my bottom, I get 9 times the square root of 9, so 9 times 3, so 27, plus 3 times 9, which is, again, 27, minus 9 times the square root of 9, which would be, again, 9 times 3, so minus 27. Oh, shoot. Then minus 27. What the heck? 27 plus 27 minus 27 minus 27. Did I write that wrong? That would be no bueno. Just a second. Sorry, looks like I made a mistake here. Alright, so looks like I got a little ambitious with my bottom line, my denominator. I apologize. So we did all this work here for nothing. I know I can hear the sighs already. So let's just set. So we're just going to actually leave our denominator as this quantity, x minus 9, times the quantity of the square root of x plus 3. We're just going to leave them separate. Which, looking back at it now, makes a lot of sense. We're going to do that because what happens with our top and bottom, we can simplify out. Now again, when this happens, it's not 0, so please don't put a 0 at the top. It's 1. So I get 1 over the square root of x plus 3. And now I can plug it in safely. I get 1 over the square root of 9, which would be 3. 3 plus 3, so I get 1 over 6. I apologize for making a misstep there. Okay. Now we're going to get into something of the limits of power functions. So limits of power functions. So first let's graph some power functions. Some easy ones like x squared and x cubed. Well, if I did x squared, as you guys know, from way back when, just a parabola, and x cubed would be that type of figure. Now again, not exact, but that rough shape. What's interesting to note is, right here, for positive exponents, so positive n exponents, the limit as x approaches infinity of just a power function will always, always, always be infinity. They are both approaching positive infinity. Whenever x is going that way, whenever we're going that way, the y is always going up. Going that way, going up. The only difference is the opposite direction. Here. So, if n even, the limit as x approaches negative infinity of xn is just going to be infinity. And if n is odd, the limit of x approaching negative infinity of xn is going to be negative infinity. Which again, makes sense based on stuff we've talked about with last lesson being end behavior, and with way back when in chapter 1 talking about end behavior. So look back at your homework from the first one. If you had an even exponent, you probably went to a positive infinity, no matter what. And if you have an odd exponent, you went to a positive infinity if you were going to a positive infinity with x, and you went to a negative infinity value if you're going to negative infinity with your x direction. Now we get to limits of reciprocal functions. Okay, the limits of reciprocal functions. Again, the most common one that we've talked about quite a bit, f of x as it is 1 over x. So it would be something like this. It's interesting to note that the limit as x approaches infinity for a reciprocal function, so a 1 over x, as we see here, actually also equals the limit as x approaches negative infinity for 1 over x, which we see here, which, as we also can tell, is just 0. We actually can use these to do some very clever algebra stuff. So example 6, reciprocal function. So let's find the limit as x approaches infinity of 4x plus 5 over 8x minus 3. Now this looks pretty scary and pretty intimidating, and the first step we're going to do is pretty weird and not something you'd be familiar with, but hopefully it makes sense after we do it. So, in this type of example, our first step is we're going to divide every single term by x. So we're going to divide each term by the highest power x. In this case, the highest power is just x to the 1. So I get 4x divided by x plus 5 over x all over 8x divided by x minus 3 over x. Now it's going to look really goofy. I know it does, but trust me. Well, if I have 4 over x, I really just have 4. And if I have 8 over x, I really just have 8. So I can write my top as 4 plus 5 over x all over 8 minus 3 over x. And again, it doesn't feel like we've actually accomplished very much, but that sets up our third step here, and it gets us into something we can work with. So instead of direct substituting, which I think we would want to do, we can't direct substitute infinity, we don't have a constant value for that. But by doing all this, we can get them in forms that are similar to the equations we just talked about. In this case, the reciprocal function. So the scalar rule says that if I have a scalar multiplied by something, I can just plug it out front. Well, do you agree that instead of saying 5 over x, that's the same thing as 5 times the quantity 1 over x? Those are the same thing, right? Just how 3 times the quantity 1 over x is there. And I still have my 4 plus and my 8 minus. Now remember, these are limits, which means that I can take my limit part and dive as far in as I would like to. So I can actually just I can break it apart as limit as x approaches infinity of 4 plus 5 times the limit as x approaches infinity of 1 over x all over the limit as x approaches infinity of 8 minus 3 times the limit as x approaches infinity of 1 over x. Well, the limit as x approaches infinity of 4, well, the limit as x approaches anything of a constant is just going to be that constant, so I get 4. The limit as x approaches infinity of 1 over x, well, we just talked about that. The limit of the reciprocal function is 0, 5 times 0, so I get plus 5 times 0. So I get 4 plus 5 times 0, so that's just 4 from my top. The limit as x approaches infinity of 8, well again, the limit as x approaches anything with no x to plug it into is just that constant, so I get 8. Then I get minus 3 times the limit as x approaches infinity of 1 over x, reciprocal being 0, so 3 times 0. 8 minus 3 times 0 is just going to give me 8. 4 divided by 8, my limit is actually 1/2. Okay. I know I kind of got smushed on this side of the board today. I apologize. I should try to leave more room because I don't know. Sometimes my camera with the stand moves a little bit. I hope that everything was caught in frame there. Okay. I hope you guys have a wonderful day, and I'll see you some other time with another lecture.